is the screencast for section 3.4, example 1. We're going to study how velocity and other rates of change take place in calculus. So we already know that the derivative of a function is the instantaneous rate of change. So we're going to look at some applications here. Part A in example 1 asks us to find the rate of change of the area A of a circle with respect to its radius. Well, a rate of change is a derivative, so we're looking for the derivative of A with respect to R, so dA dr. Like every word problem in calculus, we start out with an algebra 1 or algebra 2 basic setup. So the area of a circle is A equals pi r squared. Now I'm going to take the derivative of that to find the rate of change of the area. So the derivative of A with respect to the radius is dA dr. And pi is it's a constant, it's a coefficient out there, so I'm going to take 2 with the power rule and drop that down as a coefficient. So now my total coefficient is 2 pi. And then r is now going to be to the first power. So the change in area with respect to the radius is 2 pi r, which may sound familiar to you. That's the circumference, which also is very similar to one of your homework problems from last section. Every time the circumference, we add a little thin slice of circumference onto a circle, the area of that circle is changing. So the change in area is relative to the circumference. Part B asks us to evaluate the rate of change of A, so dA dr, at r equals 5 and r equals 10. So I want to find dA dr of 5 and dA dr of 10. So when the radius is 5 inches, the rate that the area is changing is 10 pi. And we'll talk about units in a second. And then if the radius is 10 inches, the area is changing at 20 pi. So what are the units here in part C? Well, it says if r is measured in inches and A is measured in square inches, what units would be appropriate for dA dr? Well, dA is the change in area, so that would be square inches, over dr, the change in radius is measured in inches. So we're looking at square inches per inch, which is weird, but an easier way to think of that might be square inches of area for every inch of radius. So in other words, what we have going on here is we have a circle, and at the instant this radius of this circle is 5 inches, the area is 25 pi square inches, so pi r squared. And the area is changing at a rate of 10 pi inches squared per inch. So if I add on another inch and for the radius, the new area would be 25 pi plus 10 pi, so 35 pi square inches, which you actually know would be 36 pi square inches, but it's an instantaneous rate of change. So it's only an approximation if you want to jump from 5-inch radius out to 6-inch radius. The Now Try problem number 1 asks for part A to write the volume V of a cube as a function of the side length S. So the volume is going to be the side length cubed, length times width times height, and they're all the same. B, find the instantaneous rate of change of the volume V with respect to side S. So we're looking for the rate of change of volume with respect to S, so dV ds, and I'll use the power rule on that. That's going to be 3s squared. Part C, evaluate the rate of change of V as s equals 1 and s equals 5. So I need dV ds of 1 and dV ds of 5. Now part D asks if s is measured in inches and V is measured in cubic inches, what units would be appropriate for dV ds? Well, the change in V is in cubic inches, and ds, the change in s, is in inches. So it would be cubic inches per inch, or cubic inches of volume, this time, for every inch of side length.